It's my pleasure to introduce today's speaker, Ankita Koley. She'll be speaking on dynamic content caching and delivery using Restless multi-arm bandits. Ankita is a PhD student at the Department of Electronic System Engineering, IISc. She obtained her BTech in Electrical Engineering from the National Institute of Technology, Durgapur in 2018. Prior to joining IISc, she was a commercial executive at Calcutta Electric Supply Corporation from 2018 to 2020. Her research interests include communication networks, edge caching, edge computing, and optimization. She is currently working on caching and delivery of dynamic content. Over to you, Ankita.
Thank you, Sushma, for nice introduction, and thanks to Srinai for this opportunity. So today I'm going to talk about a part of my PhD thesis, fresh caching and delivery of dynamic contents using restless multi-arm bandits. So we all know why caching is important. It reduces the response time, and also it reduces the backbone, the congestion in the backbone network. So in this work, we are interested in dynamic contents, which gets updated in the central server, and there are dynamic applications which are interested in these contents. Now, when a content is cached in the edge cache and there is an update in the dynamic update in the central server, immediately this content becomes outdated. And if you serve the content to the user, you are serving a stale information to the users, and which actually affect the QoS of the users. So users here are most interested in the freshest version of these contents. Now, if you want to serve the freshest version of the content, you have to fetch this from the central server and serve to the users. And again, this this increases the response time and also the backbone congestion. So in this work, we are going to deal with the trade-off between these two things, that you are going to deliver to somewhat fresh contents, but still you are going to minimize the latency or the response time or the backbone congestion in the network. So while discussing this talk, first I will describe some challenges that we face in this work. So let us consider an example. Say there is a request in the local cache, and the copy is, the content is there. There is a local copy in the local cache, and there is a different version of this content at the central server. So it has two options. One is that it can serve the local copy, and by doing that it will be serving a stale information, or it can fetch from the server, and by doing that it will be serving fresh information, but it will incur latency and content acquiring cost. The catch is here that it does not know what version is there, whether there is an update or not. There is another scenario, and after fetching, you are going to replace the local copy with the fresh one. There is another scenario where the requested content is not in the cache, and in that case, to serve the user, you have to fetch the fresh version from the cache, from the server, and after fetching, you have to decide whether you want to replace the content or not, because the cache has limited capacity. Also, there are other challenges, like the contents are getting dynamically updated in the server, and it does not know what is happening here, and the requests are also dynamic in nature. Now let us move to the problem that we are looking on. So I'm sorry about that. This has to be a cloud picture here. So there are n number of contents, and the cache size is m, and the request we consider follow a Poisson process, and the rate of the Poisson process is beta. Now Pn be the probability of requesting content n. Here Pn represent the popularity of nth content. For example, Z-wave distribution, which is a popular distribution in caching literature. Our model is valid for any kind of distribution. This is an example of this probability distribution. So, and that updates that are happening in the central server with a Poisson rate lambda n. This is the update rate for content n. And say we consider a tagged content, this one, and we want to measure the staleness. If you are serving the content, the cached copy of the content, we want to measure the staleness of the content, and for this we introduce a metric, that is age of version. So what it measures that number of updates since the content is fetched and stored in the local cache. Say we have fetched the content at t prime and currently we are at t, so this will be my number of updates since the content is fetched and stored in the local cache. This is age of version and this has been introduced by this Attila Relimus in 2021. Now, what are the action and cost that we model in this problem is that, so first let us consider the scenario when the requested content is already in the cache and you serve the cache copy. And the aging cost we consider is proportional to the age of version of this content. And we C is the that constant that multiplies with the age of version. And alternatively, you can decide to fetch the content and cache it. And in that case, you have to pay fetching cost. And let us consider the next scenario where the requested content is not cached. In that case, you are definitely going to fetch it. After fetching, if you discard it, whatever the other contents, existing content in the cache, you will be keeping those contents. But if you decide to cache this content, you have to decide which content you are going to evict from the cache. Now, here I am just give some annotation to these actions. Say when the cached content is requested, you have two options: serve the cached copy or fetch and cache. When the requested content is not cached, you have two options: either you fetch and cache or fetch and discard. And for other contents, there are two options: keep and evict. Since we are considering Poisson process, there are at any time there will be one request, and we consider let tk be the kth decision epoch, that means kth request epoch, and the requested content we identify by ek. Now we denote the actions at any epoch for any content is a and k. Now our goal is to minimize the average cost subject to the cache capacity constraint. Now the average cost, say we consider the total number of requests till time t is at, and first we will discuss the age cost. So let's say the age of version of the content at epoch k is Vn of k, and then aging cost is Ca multiplied by Vn of k. And here you will incur age cost if you serve the cached copy here. Now you will incur the fetching cost if you consider these actions. Either you fetch and cache or fetch and discard. And we would like to minimize this average cost subject to the cache capacity constraint, which is m in what we consider is m in our case. So are there any? Yes.
Do you assume all the lambda ends in px or no?
Yes. Yes. In this, yeah, we assume. Any other questions? Okay. This problem falls under restless multi-arm bandits formulation. Restless multi-arm bandits is a sequential decision-making problem where you are allowed to choose m out of n arms, and your goal is to minimize some average or discounted cost. And here in our work, the arm refers to the content. And in the restless multi-arm bandit framework, there is a popular heuristic. So this solving this problem optimally is probably hard. So we are actually designing a heuristic, and then there is a popular heuristic called Whittle index policy. Whittle index policy is famous for two reasons. One is it is very simple to implement. Another is under certain conditions it performs very close to the optimal one. So what does Whittle index do? It is a function that assigns values for each arm or each content, and at any point you are going to choose the index that top m indices. If you have to choose m out of n arms, you are going to choose top m indices. So how do we compute the Whittle indices? Here we solve the single content problem with holding cost. This holding cost will give us Whittle indices later. And since we are earlier in the multi-content problem, we are not considering this holding cost, but here, since there is a positive holding cost associated with keeping the content, there are two other actions that is evict the cache content and fetch and discard a content. Those are also reasonable actions. and then it gives a heuristic for the after computing the Whittle indices, the Whittle index policy is basically heuristic for the multi-content problem. And now we'll move to the single content problem with holding cost. K is epoch here. I mean, there is kth request. So M is the cache capacity. So K is varying here, M is given to you. That is here. Okay. Okay. So now we are looking at the single content problem with states and actions. So here we consider all the decision epochs. I mean, although we are considering single content, we have a tagged content, but we are going to take actions at each epoch where there can be a request for that content or there may not be a request for that content. So basically the tagged content is requested with probability P and it is not requested with probability 1 minus P. Now when it is requested says the tagged content is already in the cache, you have two options. You can serve the cached copy or you can fetch it. After serving the cached copy, you can keep or evict it, and after fetching, again you can keep or evict that content. Okay, this evict option was not, it's not available in the multi-content problem. Since we are dealing with the holding cost here, we introduce these two actions. Now, if the tagged content is cached and a different content is requested, then you have only two options: either you keep the content or you evict the content. Suppose the tagged content is not cached but requested, you have to fetch that. But after fetching, you have to decide whether you want to cache this or you want to discard it. But if the tagged content is not cached and also not requested, there are no actions. Now this is the problem we are trying to, for single content problem, we are trying to minimize. These components were earlier there also. This is the new term, that is the holding cost per unit time. And this quantity, the age of version, is not observable at the cache. Now, when you are going to serve the cached copy, the VK can be anything between 0 and tau k. I'll say what is tau k. Tau k is the time since the content is fetched and stored. And already we have the content update rate is lambda. So when you are going to when you are not observing it, that means you are serving the cached copy, it can take any value between 0 and tau k, and the expected value of the VK is lambda tau k, and your single stage cost becomes CA multiplied by lambda tau k. And when you are going to fetch the content, after fetching, your VK becomes 0. So what I am trying to say is that tau k becomes a sufficient statistic for our problem. It's not true in general, but our problem is a special case when you can replace this AOV by expected AOV. Okay. Now we solve this single content problem. It's basically a Markov decision process, and we get the optimal solution for this problem. And this is threshold based policy, and thresholds are based on the time since the content is last fetched and stored. Any questions here? Okay. So here this is the optimal. This is how the optimal policy look like when the tagged content is cached and it is requested. So here we vary the, in the x-axis we vary the holding cost, and in y-axis we plot the threshold. So below this line, you serve the cached version and keep. As you increase CH, this threshold decreases, and this is not surprising because if you increase the holding cost, you are less likely to keep the content in the cache. And above this line, you are going to fetch the content, serve and cache. And again, as you increase CH, this threshold increases. So basically, when you are increasing the holding cost, you are more likely, you are less likely to fetch, serve and cache because you are increasing the holding cost. And when you are increasing the holding cost, you are more likely to discard the content from the server, from the cache. Now when the optimal policy, in case of when the tagged content is cached and a different content is requested, So it's basically same as this part, this particular line. So below this you are going to keep the content, and beyond this you are going to evict the content. And when the tagged content is not cached and requested, there is no tau here because it is not cached here. So there is no age for that content. So it's basically straightforward. There is a constant value. If ch, the holding cost, is less than this value, you are going to fetch and cache. If it is more, then you are going to fetch and discard this. Now, when you are going to need these values, so when that in case of multi-content problem, when you have this tagged content which is cached and requested, these options are not there: serve the cached version and discard, and fetch, serve and discard. So basically you do this beyond tau star. This is the value of tau, actually tau star. Beyond tau star you are going to fetch, serve and cache, and below this you are going to serve the cached version and keep. But Whittle index is needed when there is a new request. Whatever the existing contents are there, other than that, there is a new request. That time you need Whittle indices, and Whittle index is the state of Whittle index of a state is the minimum value of ch, or the holding cost, for which the optimal action is to discard or evict the content. So let us consider we are here, and we'll draw a straight line parallel to the x-axis, and say it is cutting here, and then we'll draw a straight line parallel to the y-axis, and this will be my Whittle index value here for a given state. If it is more than tau star, then the Whittle index value will be 0 here. And for this, the Whittle index will be this particular constant I, and here I am showing it for a single content, but it will be different for different contents depending upon their parameters. Okay, and here we compare. So when there is a new request, we compare the Whittle indices of the cached content and the requested content, and discard and evict the content having least Whittle index. And Whittle index is only needed when the requested content is not cached. There any doubts? Okay. So now I am going to describe the policy. Say a content is requested, and then you first see if it is in the cache. If yes, you are going to see its age. If it is more than some threshold, you are going to fetch and cache. If it is less than that threshold, then you serve the cached copy. And if it is not in the cache, then you are going to fetch the content. After fetching the requested content, you are going to compute the Whittle indices of the requested content and the cached content, and you are going to evict the content having the least index. Okay, and you are going to replace the, say one of the content in the existing cache has minimum index. You are going to replace the new content with the that old content. Yes, sir.
The threshold, age threshold depend on the refresh rate of the content, right?
Yes, tau star will depend upon the refresh rate. Yes. Yeah.
I had a related question. So, what is the intuition behind setting the fixed threshold? Is it because you expect the content to decay, their utility to decay at a certain
Yes,
rate?
yes. So as you increase, so as your tau, that means your age of the content increases, the utility decays actually. So beyond some point, I mean, it will vary. It will depend on different contents parameters, and beyond some value, you don't want to serve this content. Okay, this is one model. There are other models also. When you are going to keep the content till certain age, you are given some threshold, and you cannot serve that content beyond that threshold. That is fixed. Okay, so that is another, that also we analyzed. Analyzed in a network, but this is a model where we consider age cost. So we say that it is decaying for linearly, but in there it is fixed for some duration. After that, it is not at all useful.
So you don't assume the knowledge of the original object being changed at the source, right? There's no
Oh, right. So basically, we don't know what is happening there. So we only know when we are fetching it from the server.
Because
I
in
mean,
real object systems, usually there is a very small cost of checking if the object or
yes,
content
yes.
has updated.
Right, right. That is there, but here we are assuming that you don't know what is happening in the server. But that work has also been I mean studied, that they consider that as a poison process. You have a say alpha with the poison process, alpha is the rate, and you are going to check the server continuously what is going to happen. I mean, if there is an update or not. Okay.
Yeah, so it might be a redundant question, but anyways, I'll ask. So age is the only parameter that is depending whether a content is evicted or kept,
Yes,
or is there any importance or significance that is associated? Like I have a very important content, and probably it is okay for me to wait beyond the threshold.
okay, so this the importance of the content is given by the popularity also, request rate also, how often it is going to be requested, how popular is this content, and this tau will depend upon everything.
Okay.
Okay, so now I'm going to compare this policy. This is so what they do is that I mean basically solve the same problem, and here they define some popular set of contents, and they cache only those contents, and they periodically update those contents. This is the work by Attila Relimus, and when we apply the Whittle index policy, it performs very, much better than their policy, because the reason is their policy is kind of static policy. Okay. Now, given that, so how close it is to optimal. So I have not described what is relaxed RMAB. It's basically a lower bound. We don't know what is the optimal value of the optimal solution of the multi-content problem. So it actually works as a lower bound of that original optimal problem. And Whittle index policy is, performing exactly same as this, means that it performs exactly same as optimal, because it is coinciding with the lower bound. Okay. Now, we actually added one more action here as an extension to this problem. So that is earlier you have to serve the content when there is a request. Now you have another option. Okay, so suppose you have a stale version and you don't want to serve that content to the user. So what you are doing, you are saying that you are telling the user you wait for some amount of time. When there are enough requests, I am going to fetch it from the server and I am going to serve the fresh version to all the requests. So what happens that when a request comes, you keep them waiting at the queue, and again you keep them waiting, and after certain amount of request, if you feel that okay, I have enough request, then you are going to fetch and serve from the content. And this is we design as a waiting cost. So here the waiting cost is that a constant, I mean it's proportional to the sum of q of the all the contents. So the local cache will have a queue corresponding to each content, and the waiting cost will be proportional to the sum of the queues. And again we have the options of serve the cached copy, where it will be aging cost. It will be there will be incurring aging cost, and then will be fetching and serving from the central server. There will be fetching cost associated with it. And again we are trying to minimize the average cost subject to the cache capacity constraint. Any questions about the model? Okay. So we are so I am directly discussing the single content problem, because again we are going to design a Whittle index based policy. So this is exactly same as what we had in the previous problem. The new thing is that the wait action. So here it's not only wait action, it's wait and await. It's because when you take the wait action, after taking the wait action, you are not going to take the serve the cached copy option. You are not going to exercise this option, because that will not be optimal. Okay. So if you take wait action after certain point, after certain time you are going to fetch the content. So since you are not going to use the content, you are going to evict the content because there is a holding cost associated with the content. Okay, and similarly here also, when the tagged content is not cached and requested, other than these two actions, you can also exercise this wait action here. Now here, since you are going to wait and evict this content, you are directly moving to here or here because now you don't have the content here. Okay, so whenever you are in this state, your queue length is going to be 0. You are going to have I mean this tau, the time since last fetch and stored, this value can only be positive. Similarly here also, but here you will not have tau, you will have the state as the queue length. So the queue length is positive only in this case. Here the queue length is 0. Okay. And that's why we could compute the Whittle indices because at any point it depends upon only one parameter. Okay. Now I'm directly going to this single content problem solution. Now when the tagged content is cached and a different content is requested, then again this threshold is based on tau. But when the tagged content is not cached and it is requested, the threshold are based on the queue length. Okay. Here it's similar to the previous problem. Beyond some tau we are going to evict depending upon the value of holding cost, and below some tau we are going to keep the content. Here you are going to wait until some queue. Okay, so beyond q hat you are going to and beyond this value of I you are going to anyway wait, and beyond q hat and beyond q hat and beyond I you are going to fetch and discard. But this below this threshold, below this value I, you can either wait or fetch and keep. And as you increase the value of ch, you are going to wait more and more. Okay, and from this we compute the Whittle indices, and this is the minimum value of ch for which it is optimal to wait or evict the content. Okay, now let's say requested content is in the cache, and then you are going to see the age of the content. If it is beyond tau star, if it is below tau star, you are going to serve the cached copy. If it is beyond tau star, you are going to see the queue length also. If queue length is below some threshold, you are going to wait, and if it is more than some threshold, you are going to fetch and cache. Again, this will depend upon all these parameters, popularity, and then its request rate, update rate, everything. Yes.
Fetch and cache, does it mean, is there a delay in fetching the object?
Yes, there is a delay.
That
So when you are going to fetch, you are going to serve all the requests.
So do you model the delay in fetching the object when you decide to?
Okay. So this is the waiting cost. I mean the queue length will contribute in the waiting cost. In between request and fetching, your this request will be queued, and there will be a cost associated for this delay. That is the waiting cost, and that will be proportional to the sum of the queue of this corresponding contents.
So not exactly the original problem, but have you also looked at the policy where you proactively fetch the object because you know that with high probability you are going to fetch that object? So
proactively means that server will send you the contents to the, server will decide when to send the contents to the,
or the client will ask for the refreshed content, because I know that I am likely to get the object request.
Okay. No, so when you are going when you get a request, then only you decide whether you want to fetch or not. Okay, so here we are not predicting that when you are getting a request or not. Okay. So when the requested content is not in the cache, then you compute the Whittle indices of the requested content and the cached content, and say the other content has the minimum index, and in that case you will be fetching the content and cache and replace whoever has the minimum index here. But if it is, and you are going to evict the this content who has the minimum index. But if it is not the case, then again you are going to see what is the queue length, If it is more than some threshold, then only you are going to fetch, and after fetching you are going to discard it because it has the minimum index, not any other content. And if it is less than that threshold, you are going to wait. You are going to wait for some request before you are going to fetch the content. Okay, any questions? Okay. So I'm going to finish my talk in 30 minutes. So, okay. So this problem, I mean, we're the first one to study this problem. So we actually designed this policy, myopic policy. This is kind of greedy policy. So what we do is that you are going to maximize the single stage cost, but also you are going to serve all the requests in the next slot. You don't want to keep, because when we only maximize the single stage cost, it performs really bad. So then we realize that you have to serve all the requests which are waiting. Then we got this policy anyway. So here again the lower bound, it performs really close to the lower bound, and this is our Whittle index based policy. And here we compare with our previous problem. So see, this is without Q that we discussed earlier, and here we increase the value of waiting cost, and when the value is the least, it performs better than this. I mean, it's not surprising because you are adding one more action, so it will perform anyway better, at least as good as this. And when you increase this waiting cost, it becomes closer and closer to the fresh caching without queue. And beyond a certain value of the waiting cost, it is not going to perform better than this. So beyond certain value of CW, it is going to merge with the optimal cost, average cost for the fresh caching without queue. So basically what is happening here, you are not anymore exercising the wait option. You are going to either serve the cached copy or serve the or fetch and serve the fresh version. So we study this optimal content fetching and caching problem, and then we derive this Whittle index based policy that outperforms the existing work. And we have another two extension here. One is that local cache is connected to the central server via wireless channel that we already also have solved. And here another problem, this wireless channel between local cache and users. This is another extension, and this recently got accepted in transactional networking. And thank you for attending my talk. Any questions? It is correct. So how do you suggest, how do you remodel this because here we proactively fetch it. Right. Yeah, and we also know the request rate and probability. Right. Yeah, that way, yeah, can do. But also we assume here that we know what is the update rate here, and also what is the all these parameters, So there are also a series of work where you learn the Whittle indices. So there you do Q learning, and you update the Q values, and also you update the Whittle indices there. So there is another extension of this work which we have not yet exercised. Okay. So you're going to look at how much it has changed. Yeah. So, and then you are going to decide how you are going to, if you are going to fetch the whole. But for that also you are going to fetch something. Right. Right. Yes. So it is. I don't know. It is. how it is different from checking there is an update or not? You have to again check all that. I mean, you have to, okay, okay, yes, right, right, yes, right, right. Mm-hmm. Okay. So will not it be the say I am talking about the Facebook CDN. So it will be at the Facebook server, right? So multiple, you mean multiple servers from the Facebook only? Ah, okay. Right, right. Yes. Mhm. Right. I think it will help modeling that. Yeah. Basically, I am quite interested in the delta thing that you're fetching a variable amount of data to see that how much update. And actually, that is a more realistic thing to do than checking the updates or waiting. I mean, fetching based on the age how long it has been there in the content. Thank you.
More questions about some of the modeling assumptions. I think you had a linearly increasing.
Linearly, right, right.
Would a more realistic assumption be you have a certain value for an item when it starts with age 0 and it decays exponentially at some rate specific to the item, or some of the decay rate is fast, or others it's slow?
So actually, instead of linear, if we consider the convex, it will be more complicated, but it will work actually.
But your cost increases unbounded,
On
whereas maybe your total value for some item of news is fixed, and if it's
oh, the cost is increasing. Yeah.
the value goes to 0, so the cost shouldn't go above the fresh value of that.
Oh, right. So you are saying that cost is increasing, but the value is fixed. I mean, the when we're it is linear. Now I'm.
For me, it's okay. So I ask you for the latest cricket score, and
Uh-huh.
you give me some old score.
Right.
The cost to me is not trying
Yes,
to
yes.
have the value of knowing the score at all. You could have
No,
said,
that
I
is
don't know,
right.
and then
Right. Yes. So for this cricket score, I mean, which are really real time, those are pull based. Sorry, push based. Their server will send you that where, or central server will decide when to send you the data. So here the applications we're considering, it's not.
that wasn't a, I mean,
Yeah, I understand.
gave
Yeah.
the first example.
I mean that what I'm trying to say is that for this kind of data, pull based model will be more viable than this kind of proactive fetching. Anything else, sir?
I guess the hardest question is, okay, if you know all these things, yes, you can solve the problem.
Right.
But
Yeah.
if you don't know,
Then we have to learn them, and there will be two kind of learning: model based, model free, and then you have to see how it is going to be. The Whittle index, I mean, computing the Whittle index will be a mess in that case. I mean, even learning the Whittle index will be a mess in this case, because we have infinite horizon problem, and the tau can vary from, I mean, it is continuous time. Uh, so we have another problem where your tau is finite. So if it is below some value, say f, that is useful, and the value is same from 0 to f, and beyond f it does not have any value, and we thought of doing learning there. And then what we did, we considered network, tandem network, and we solved that problem, and then we did not go to that learning part. We did not. But these are interesting questions that I mean, in real life we don't know what is the popularity, what is the request rate, or what is the update rate in the server. and there are algorithms to do learning, but how good it will perform, it will, I mean, we have to see.
Thank you, Ankita, for the short and interesting talk. Thank you, everyone, for attending, and we have arranged refreshments in the coffee hut. Please have them.